In the last video, we derived the conditional probability formula, or not so much derived as demonstrated it, and we showed the following. That the probability of A happening given that B happened is equal to the probability of A and B happening divided by the probability of just B happening. Now, this has different applications. Unfortunately, some of the examples in textbooks seem to be quite trivial around this kind of notation, but there are real-world situations where this is very useful as a formula to have. Here is a demonstration of a problem where we can use this. Whether this is realistic or not, I don't know, but it's a good example of how we can kind of use this formula to find probabilities that might not be obvious from a probability tree. So let's have a look at this example. A machine A produces 20% of the toys produced in a factory. 10% of the toys produced by this machine are defective. It is known that 22% of the total output of this factory is defective. If a particular toy is selected at random and found to be defective, what is the probability that it came from machine A? Now, besides this being a crap toy company, where 22% of their output is defective, that's probably not optimal. We're still going to do this probability. The probabilities maybe are a bit high, but we can still, do this problem. It's good to have, not tiny, trivial probabilities going on here. So what I'm going to do is, again, I'm going to draw a probability tree to represent this. First thing we need to look at in this is what machine produced this. So we're told that machine A produces 20%. So the probability of A is 0.2, whereas that means that 0.8 of the toys must be not produced by A. Okay. Now the next bit we're told is that 10% of the toys produced by this machine are defective. So this is saying that the probability of being defective given it was made by A is equal to 0.1. Okay. So if we think about whether it's defective or not defective, 10% are defective, 90% aren't defective. Similarly, we don't know anything about the other machines just yet, but either they're going to be defective or not defective. What we are told is that 22% of the total output of the factory are defective. So the probability overall of being defective is equal to 0.22. Now, we're going to have to work a little bit backwards here because the bottom line is we don't know what these probabilities here are. If we wanted to do that, we could do the following. Okay. This probability of overall of being defective is equal to the probability of it being defective and coming from A plus the probability of it being defective and not coming from A. That kind of makes sense, doesn't it? That overall probability of being defective is the sum of the probabilities of being defective from each place. Now, what we can do is we can work out this because we know about machine A. So the probability of being defective and A, I should have put these on earlier. Probability of being defective and coming from A is these two things multiplied together. Okay. So this is 0. No, it's not. I marked that up. 0.1 times 0.2 is 0.02. So what we have is that 0.22 is equal to this thing here. Probability of being defective is 0.22. Probability of being defective and from A is 0.02. The probability of being defective and not being from A, we can now work out because this is an equation. What I'm going to do is I'm going to subtract 0.02 from both sides, and I end up with the probability of being defective and not coming from A is 20%, 0.2. So that's what goes here, and this goes there. Okay, the question though asked, if a particular toy is selected at random and found to be defective, what is the probability that it came from machine A? So what I'm being asked here is, what's the probability of that a particular toy came from A, given that it is defective? So I'm looking at the output, I find a defective toy, I want to know how likely was it that that came from machine A. Now notice this probability is not present anywhere on my probability tree. This represents the probability of A. This is the probability of not A. This represents the probability of being defective given A, not the probability of being from A given it's defective. These are different things, okay? Similarly, these ones represent other things. They don't represent this. To solve this, I need my conditional probability formula. So this is how I solve this problem. The probability of coming from A, given it is defective, is the probability of coming from A and being defective divided by the probability of being defective overall. Probability of coming from D and being defective, coming from A and being defective, is 0.02. Probability of being defective, we said was 22% is defective, or 0.22. Solving that, I get 1 in 11. So there is a 1 in 11 chance that any particular defective product came from machine A. Now I realize that a lot of this is some heavy notation. This is why we spent a good chunk of time last week spending a lot of time getting our heads around this kind of notation. It is really important that you, if you didn't understand this, that you work through that problem again and come with your questions this week to class so that we can try and answer some of those questions that you might have.